This video is going to cover the concept of circular motion. There are two things that we talk about in regards to circular motion. One of them is linear speed. Um, Linear speed, key phrase there in like root word there in linear is obviously line. So this is the rate at which the distance traveled is changed. Okay, the rate at which the distance traveled is changed. Linear speed is equal to distance divided by time. Okay, that is what you've known forever. Okay, so distance equals rate times time. If we're looking for the rate, okay, so that's distance divided by time then is equal to your rate, which we refer then as linear speed. Okay, angular speed is the rate at which the central angle is changing. Okay, angular speed is radians in the angle divided by time. We're always going to do this in radians. Okay, so radians divided by time. So if we should give you an idea of what we're talking about here, as we take a object. So what I've got here is like you've got a string on a attached to a rock or something that can keep like a rope or whatever taut, and you're spinning that, okay, in a circular motion. When we do that, okay, there are two things that are happening. Obviously, the rock or whatever this weighted part on your string is moving at a particular rate. Okay, the idea that we want to think here is if I were to convert that circular motion of that rock and how fast it is moving in a circle into how fast it was moving in a straight line, that would be referred to as linear speed. Okay. If we look over here, this is kind of the bird's eye view looking down on this circle. You can see that this angle here is changing as that weight moves around in that circular pattern. So as that is changing, okay, that is radians changing per time, that is what we're talking about when we talk about angular speed. Okay, it's how fast that green angle is changing. Okay, so we want to know how fast is this object actually moving if it were moving in a straight line, and then how fast is this angle changing as that circular motion takes place. So suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t. Let s equal r theta. Okay, that's the arc length formula. Okay, b the distance the point travels in time t, and that's really what we've got going on here. If we look at this right here, well, let's see if I can trace that. There we go. Okay, so however long that was, so let's do it again. If I say, I'm just going to count here, 1 Mississippi, 2 Mississippi, 3 Mississippi. So if I count 3 Mississippi, 3 seconds, okay? This arc is the distance, okay, that object traveled in 3 seconds, okay? We should be able to find that distance by taking r, which is our radius, times theta, which would be the angle that was traversed. And that will give me that distance. Okay, and then I can take that distance and divide it by time, and that will tell me how fast that object was moving in that circular motion. And that's what we're getting right here when we say linear speed. It's s, which is arc length, divided by the time that arc length was essentially generated or created in that applet, and that will give me linear speed. We denote linear speed with v. Okay. The angular speed is how fast that angle was changing. So how fast was that green angle changing over those 3 seconds? Well, how much did it change? In this case, looks like it's saying about 220. So 200. I'm gonna say, I'm just gonna estimate. I'm gonna round it to 210. So if I'm gonna round it to 210, that ends up being 7 pi over 6 radians. So it takes 7 pi over 6 radians. That was the theta. That would be the angle. And I divide it by 3 seconds, and that will tell me how fast that angle is changing per second. So those are our two formulas that we're going to talk about. So this weird looking W here is actually omega. Okay, that's a Greek letter or lowercase letter for omega. Like obviously theta divided by T. Here we've got V equals S divided by T. I just thought maybe it might be appropriate as before we get too far into the course, if there's ever a symbol that you're not aware of or you're uncertain about, you can do a quick Wikipedia search, Greek letters, Greek alphabet, whatever. And we're going to primarily use the lowercase letters. So you can see we've used alpha, beta, we've got gamma here will be common. Delta, you guys have seen capital delta before. Here's lowercase delta. Epsilon is something that we would use in calculus quite a bit. Zeta, there's your theta. You've heard probably the word iota before. Kappa, lambda. If you're in science, you've probably used lambda quite a bit. Physics. Obviously mu. Pi, rho. These are common. Greek letters that we're going to use in trig. Sigma is used quite a bit in stats. Mu, I said obviously mu. We're working with mu in stats right now. Phi, it's a common letter to be used in differential equations and differential geometry. In omega, so here we see omega, lowercase omega. So I think it's important maybe to familiarize yourself with those. Don't let them scare you. They're just variables. Instead of using x and y, we use these Greek letters because they're a different set of variables. They kind of attach themselves, and at least in this course, to being angles, measurements of angles. So we've got these two formulas. Theta is always going to be 2 pi times the number of revolutions. Okay, so sometimes that number of revolutions might be, I'm not sure what that is. That number of revolutions might be multiple. Okay, it might be more than one. It could be 2, it could be 3, but it could be just a portion. Okay, it doesn't have to be an entire revolution, kind of like this one here was. Okay, so there I said 7 pi over 6, if this is 210 degrees, that'd be 7 pi over 6. Not quite 2 revolution, or not quite 2 pi, not quite 1 complete revolution. But as we do any of these problems, when we need theta, theta is going to be 2 pi times the number of revolutions. Here it says a boy rotates a stone in a 3-foot long sling at the rate of 15 revolutions every second. Find the angular and linear velocities of the stone. Okay, so I like to draw a little picture. So we've got our stone, okay, and it is going to be moving along this circumference, okay. I like to draw these tangent lines to give me the idea, kind of like that image here was doing. Okay, that tangent line is showing the direction. That's why sometimes we call it velocity instead of speed, because that's showing a direction that this object is moving at that time. Velocity is defined by speed with a direction. The idea of that tangent line is if this is that rock in that sling and he lets go, that rock will take the path of the tangent line. Okay. Obviously, if he doesn't let go, then the forces at play here are going to keep that rock moving along the circumference. But the stone in a 3-foot long sling, so my radius here is 3 feet. Okay, it's at a rate of 15 revolutions every 10 seconds. Find the angular and linear velocity of the stone. So angular speed, omega, is equal to theta divided by t. Okay, so theta, like I said, it's the 2 pi times the number of revolutions. Okay, so 2 pi, number of revolutions we're doing is 15. And we're doing this for 10 seconds. Okay. So then we're going to take 2 pi times 15, so that's 30 pi radians per 10 seconds. So that's going to give me then 3 pi radians per 1 second. Okay, so what we're saying here is that that angle, if this was the situation here, that angle right here, this green angle, would be changing 3 pi radians, so it would be 1 complete revolution and then half another revolution, that would be 3 pi, every 1 second. Okay, so it's doing, see if I can get this to stop back at the, maybe I can just reload this, refresh it. There we go. Still not where I want it though. There we go. Close enough. So we would, if we just keep track of this, I'm going to let this play. There's 2 pi, 3 pi. Okay, so you kind of seen how fat or how long that took. Okay, or the rotation that it took. So 3 pi would have been that far, that big of an angle, and this is saying that it would have been doing that rotation, that 3 pi radian rotation, every 1 second. Okay. Linear speed is s divided by t. Okay, now s we don't know. Remember, s is arc length. So that is found by taking r theta. Okay, so r is the 3 feet. And theta, remember theta was the 2 pi times 15. Okay. So 2 pi times 15. So obviously that's going to give me 30 pi times 3. So 90 pi feet. Okay. So that is S. So now I'm going to go 90 pi feet and we're doing this in 10 seconds. So we're going to get 9 pi, the 90 and the 10 cancel out, feet per second. Okay. Now, 9 pi feet per second, that might not be something that we're real accustomed to. How fast is that? 9 pi feet per second? That doesn't even make a whole lot of sense right off the bat if we think about it. But if we do this, 9 pi feet per 1 second, let's change this into something we're more comfortable with. We're more comfortable with miles per hour. So let's take feet and get that into miles. So we know 5,260 feet for every 1 mile. So feet will cancel. And now let's get seconds into hours. So we know that let's go like 60 seconds will equal 1 minute. So seconds cancel out. Times then, if I go 60 minutes for every 1 hour, the minutes will cancel out. So now let's take that, open up Desmos here, multiply this out. So we've got 9 pi times 1 over 5260 over, or times 60 over 1 times 60 again. Make sure that was it. Okay. So then everything canceled out. We left with miles per hour as the only units left over here. And we're seeing that rock would be traveling at 19.35 miles per hour. And that's the idea that if it was moving in a linear direction, 19 point or 19 point whatever 0.3 miles per hour. There's a relationship between linear and angular speeds. Okay, and it's a pretty obvious relationship. I think if you do a little bit of algebra here, we know omega is equal to theta over t. We know that linear speed is equal to s over t. Okay, distance essentially divided by time. But we know s from right here, and what we talked about yesterday, is r theta. So if I replace that with r theta, I get something like that. So I can say v is equal to r theta over t. But look at this here. Theta over t is exactly the same as omega. So what we can do is say that linear speed is actually r times omega. Okay. So we already figured out linear velocity here was 9 pi feet per second. Let's see if we can come up with the same thing using this relationship. V, linear speed, is equal to r, which was 3, times in omega. We found omega to be 3 pi radians per 1 second. 3 pi radians per 1 second. And remember, this 3 was in feet, so 3 times 3 pi is 9 pi radians per second, which is exactly the same thing we found. Oh, I said pi radians, should be 9 pi feet. Okay, now a lot of people say feet radians, or it should be feet radians when we think about it that way, but radians is a dimensionless unit. So when it's coupled with a distance, we just let it kind of dissolve. So that matches up with what we found as linear velocity using that formula. This formula tends to be a little bit easier, a little bit more fluid to be able to use, and we'll probably use that one predominantly, r times omega. Number 7 says a woman is riding a bicycle whose wheels are 26 inches in diameter. Okay, so we got a bicycle wheel here, 26 inches in diameter. So that means that the radius is 13 inches. Okay? It says if the wheels rotate at 125 revolutions per minute, okay, RPMs, find the speed at which she is traveling in miles per hour. Okay? So what they're asking for here is the linear speed. Linear speed is equal to R times omega. Okay? Omega is theta divided by t. Okay? If you remember what theta was, theta is equal to 2 pi times the number of revolutions. So 2 pi, 125 revolutions. So that's 250 pi radians. Now it says per minute, so over 1 minute here. That's my omega. So then, or sorry, that's my theta. My omega, let me retract my statements. 250 pi radians is theta. That is how fast this angle here is changing as that wheel is moving. Okay. When I divide that by 1 minute, because it's revolutions per minute, that gives me that right there. It's a theta divided by a time. So my omega is 250 pi radians per 1 minute. So now if I want velocity, linear velocity, it's radius, which was 13 inches, times 250 pi radians per 1 minute. Okay, so we don't go in because I don't know what it means. So the radians is, like I said, it's dimensionless. So when we're done here, whatever 13 times 250 is, I don't really care. So 13 times 250 times pi. My units would be in the top. Inches were the only thing there, and minutes is on the bottom. Well, I don't inches per minute. That's not a rate that I'm accustomed to. So I'm going to figure out, I want to go miles per hour. So it's dimensional analysis. I always give myself a little bit of room and write down the units that I want to get to. If I know my target, it should make things easy for deciding what to cancel here. So I want to get inches to go away and get eventually miles to show up. So inches need to be on the bottom here to get them to cancel right away. But I don't know a direct link from inches to miles, but I do know one from inches to feet. So 1 foot, 12 inches. The reason I went to feet because I do know how to go feet to miles. Oh, 1 mile is 5,260 feet. Okay. So now feet are canceled. So now all across the top I'd have miles left over. On the bottom, okay, I'd have minutes. I don't want minutes, I want hours. So I'm going to put minutes here. That minute and that minute will cancel. And there is a direct link to hours. So 60 minutes for every 1 hour. So when we type that in, 13 times 250 times pi over 1, so I didn't really put over 1 there, but times 1 over 12 times 1 over 5280. I don't know why I wrote 5260. I think I might have even done that up here. Yeah, 5,280 feet in a mile, not 5,260. It's late. And then times 60. So that's going to be 9.668 miles per hour. Okay, and again, that's something that we can relate to that distance a little bit easier than something in regards to inches per minute. Now, if you left it as inches per minute, so this 13 times 250 times pi. Okay, that's inches per minute. Okay, but these are both rates, inches per minute. So if two people started at the same spot and one rode rode their bike at 9.67 miles per hour, and the other one rode their bike at 10,210 inches per minute, and they both started and stopped at the same time. So maybe they're both riding for like 2 minutes. They would both finish at the same exact spot. They would both travel the exact same distance. Um, but this one, we understand that we've traveled 9.66 miles per hour recently. Okay, we're accustomed to that. We're not accustomed to that. We've traveled this recently, but we've never viewed it that way. Okay, in those dimensions. You're going to see questions in your homework very similar to those. Um, they're going to ask, it could be, we've got a bike and there's a tire, an air valve on that bike. And they might ask you, how fast is that air valve moving? Okay. Basically, what they're doing is asking, what is the linear speed of that air valve? You might see a question where they have like a saw blade, and they have a tooth of the saw blade, and they want to know how fast is that saw blade moving. So they're asking, what is um, the linear velocity, omega, times your radius? That's what they're asking. How fast is that thing moving? Even though it's going in a circle, and it's never gaining ground, it's repetitively rotating the same location over and over and over again. But that thing is moving at a speed. They want to know, what is that linear speed. Okay. Same thing. So they'll ask the question with like a ceiling fan, and they'll tell you that you got a ceiling fan with a blade length of like 40 inches. And they'll ask you, okay, how fast is the tip of that blade traveling? Okay, so these are all very similar style questions when we talk about angular and linear speed, angular and linear velocities.